Hello, today we're going to be going over 3.8, the common ion effect. This is the trickiest part of the solubility unit 3 notes, so just make sure you're reading through these, following along carefully, and you're doing all the practice problems. So in the last sections, we talked about how our solubility depends on our ion concentration when a substance is dissociated in solution. And it could be related back to the product of our ion concentrations, which is our KSP value. We're going to be looking at today what happens when we change the concentration of one of the ions that's involved in our equilibrium. So we talked about before how our solubility can be altered by temperature, changing our temperature. For example, for most products, the higher the temperature, the more we can dissociate our ions into solution. So changing the temperature, if it changes our product concentration, will then change our value of our KSP. So it's the same when we're talking about our KEQ. Remember, temperature is the one thing that can change that KEQ value. So it's the same when we're talking about solubility. The one thing that can change our KSP value is changing our temperature. Remember that changing our concentration of a species will not change our KEQ value. So just the same here, it's not going to change our KSP value. So in this section, we're going to look at how we can change our ion concentrations in solution and change our solubility. So how much can dissociate, but our value of KSP does not change. So in this section, we're talking about common ions. So what does that mean? Well, common usually refers to either two things, ordinary or shared. We're going to be talking about the second meaning here. So if you're talking about common common factors in math, you're looking at variables that are shared between two different terms. So the same thing is going to be going on here when we're talking about common ions. It's an ion that is shared between two different sources. So if I'm looking at silver chloride and magnesium chloride, when these dissociate, if they dissociate in solution, my common ion is going to be the chloride ions. So let's look at how these can affect solubility. So we're going to be considering the solubility of just regular table salt, sodium chloride. So in a saturated solution, our equilibrium is going to look like so. We'll have our sodium chloride solid that's being dissociated into sodium and chloride ions. All right, now, according to Le Chatelier's principle, I have the equilibrium up here, any increase in the ion concentrations, so our sodium ions or chloride ions, will then cause a stress, which will then have to shift the system to the left in order to get rid of that stress or decrease that stress, right? We're still in equilibrium, so Le Chatelier's principle is always going to apply here. So a shift to the left will mean that our precipitate will occur and therefore be less soluble than it was before. So for example, an increase in the concentration of sodium could be implemented by adding some sodium nitrate, for example. Our nitrate ion and our sodium ion would dissociate. Nitrate is a spectator ion, but our common ion here is sodium, so that would be involved in this above equilibrium. Similarly, if I added some calcium chloride, my calcium does not react with any of this, but my chloride could be involved in my above equilibrium, increasing my chloride concentration and perhaps driving the reaction back to the left. So this is the common ion effect. We're going to look through and work through a sample problem. It's quite long, but it does have many different parts to it. So in general, the addition of a common ion, so adding one of the ions that have dissociated, is going to act to decrease our solubility of a compound, because according to Le Chatelier's principle, it's going to shift the system to the left towards the precipitate. This means that there'll be more ions in solution, so less will be able to dissolve or dissociate. So we're going to be looking at the solubility of strontium sulfate in 3 different conditions. The first condition is dissolving how much strontium sulfate can dissociate in pure water. Then we'll be adding strontium sulfate to a 0.1 molar strontium nitrate solution. And finally, how much strontium sulfate will be able to dissociate in 0.1 molar chromium sulfate. So those are my 3 different solutions I will be dissociating this salt in. Let's see how their solubility changes. So first I want to look at my KSP. So it doesn't matter if I'm going to be changing my concentrations, because all of this is going to take place in the same temperature. My KSP is going to be the same for every single condition. I can find my KSP by looking up my strontium sulfate here on my table. So 3.4 times 10 to the negative 7. So before we dive into any actual math, let's just look at what's going to happen from a qualitative analysis. So we have our equilibrium equation of our strontium sulfate. That is our solubility, what's in question here. So this will always dissociate into some strontium ions and some sulfate ions. And from before, our KSP, just to have it on this side, is 3.4 times 10 to the negative 7. So in our first example, when we're adding strontium sulfate to pure water, this is going to be used as a control. We're only going to be dealing with this equilibrium equation. We aren't going to be adding any extra ions. In our second, our strontium sulfate is dissolving in strontium nitrate. So here, if we just draw our strontium nitrate solution, what's going to be happening there is our strontium nitrate is going to dissociate into strontium ions, make sure this is balanced, and nitrate ions. So therefore, I'm already going to have strontium in solution, so this is going to add an increase to my strontium ion above. So here my strontium ion will be the stress. If I'm increasing my strontium ion concentration up here in this equilibrium, this is going to cause my equilibrium to shift to the left. Therefore, qualitative prediction would be that my strontium sulfate is going to become less soluble than above, because now I have this added strontium ion, which will shift my equilibrium, shift it to the left towards the precipitate. So I already have some strontium in solution. It makes sense that my strontium sulfate would now be less soluble than in pure water. All right, let's look at the next condition. So much like before, I am adding it to a solution that already has some of these ions present. Let's look at chromium sulfate here. What's going to happen in this solution? This is chromium 4, so we have the 2 on this sulfate. So in the solution, this will dissociate as well. I'll have my chromium 4 and my sulfate, making sure this is balanced. So here, my sulfate ion is going to be the one that's causing the stress. An increase in the sulfate, once again, is going to cause a shift to the left. So it should make sense that my solubility of strontium sulfate will decrease. However, how is it going to decrease compared to my strontium nitrate? Well, both of these, I have a 0.1 molar solution. So let's look at my coefficients here. If I had 0.1 molar of strontium nitrate, that means I'm adding to this above solution 0.1 molar strontium ions. This is a 1-to-1. However, looking at my coefficients here, if I have 0.1 molar chromium 4 sulfate, I am now adding 2 times that amount. So I'm adding 0.2 molar of my sulfate ion. So I'm adding more sulfate as a stress here, actually double the amount of concentration than above in my strontium ions when I was adding those. So therefore, in my my strontium sulfate in this solution here should be even less soluble. So I will be able to dissociate less of my ions when added to 0.1 molar chromium 4 sulfate because there is more sulfate ions in solution, which is my common ion. So it is less soluble in this condition than it would be if I had added it to strontium nitrate. Because my strontium nitrate, even though it's adding strontium ions, it's not adding as much as my sulfate down here. So that would just be qualitative. Here, sorry, this is supposed to be quantitative. So this is just more looking at the theory. Now let's actually get into the numbers. What is my solubility in each 3 of these conditions? So here I'm going to be using KSP. So in pure water, so we are just involved with our strontium sulfate dissociating into strontium and sulfate ions. So I'm trying to find out my solubility here. However, this is a solid. It is not going to take place in my KSP expression. I am going to say I will let X be equal to our change, or our, sorry, let's say our final amount of strontium concentration at equilibrium. Now, I have set up an ice table here, but just like before, we don't need an ice table. All of this is going to dissociate, and we're not going to have any sort of added change here. So I don't really need an ice table. So let me just work on that final line of the ice table, just as we've been doing before. So if I had 0 to start with, oh, sorry, I wasn't going to do that. If this is X 1 to 1, this is also going to be X, and this is not applicable. So whatever this amount is when it dissociated, if I have X amount of strontium ions, I must have X amount of sulfate ions because this is a 1 to 1. There's no coefficient here. And I don't need to worry about this because it's not even involved in my KSP. So now I can write my KSP expression, which will be my strontium ions multiplied by my sulfate. And I know what this KSP was from before. So 3.4 times 10 to the negative 7. This is equal to X times X, so X squared. I will square root both sides. And I'm left with X is equal to 5.8 times 10 to the negative 4. Now this is my value of X. This is up here. In my dissociation equation, for every 1 mole of strontium sulfate, I get 1 mole of strontium. So this actually ends up being my solubility of strontium sulfate in, we'll say, moles per liter. So this is my value of, this is my solubility, how much in a specific volume of strontium sulfate can be dissociated in pure water. So let's look at how this changes in our different conditions. So far this question has been the same question that we've been doing all throughout these units. Well, let's look at another one. So now what's going to happen when our strontium sulfate has been added to the strontium nitrate. I'm just going to write that down. We're going to have both dissociation questions here, or equations. So here is my initial balanced strontium nitrate solution. And in this defined variable, let's put our actual solubility in question here. We have our strontium sulfate, strontium, and sulfate. So because I'm wanting to find the solubility here, much like before, I need to allow my variable to relate back to that solubility. So I'm going to say let, once again, x be equal to the change in my strontium. The reason I'm going to say it's change, because initially I will have something already there. So in these cases, and these are the only cases, the common ion effect, you will have to actually set up an ice table, because you won't be dealing with just nothing to start with. You're already going to have an ion in solution. So let's set up our ice table. And this is done in the same way that our ice tables were done before. So we have our initial, our change. This is a solid, so we do not need to worry about it. So to start with, let's say even before adding our strontium sulfate, before it's dissociated, we have absolutely no sulfate ions in solution, but we do have an amount of strontium. And the strontium is coming from our already strontium nitrate dissociated solution. So if I have 0.1 molar, this means I have 0.1 molar strontium ions and 0.2 molar nitrate. Now my nitrate is a spectator. It is not involved in anything else I'm doing. I don't need to worry about it, but I do have this 0.1 molar strontium ion already. Now for my change, this is when my strontium sulfate has dissociated. So I've added plus X, this is a 1-to-1 plus X. So now at equilibrium, I have X amount of sulfate, but 0.1 plus X amount of strontium. So I have more strontium in this condition than I had before, which should make sense because I already had strontium ions present. So now let's write our KSP. So our KSP has not changed. So as long as our temperature has stayed the same, our KSP value is always going to be the same. So it is still 3.4 times 10 to the negative 7. Now I have that this is equal to 0.01 plus X and X. Now this math could get a bit funky. We're not going to actually deal with any quadratics. We're going to find a way to kind of get around this by using what we know about significant figures. So it's safe to say that since strontium sulfate is only slightly soluble, not much is going to dissolve. So in our last question, in pure water, we had only 5.8 times 10 to the negative 4 moles per liter being able to dissolve. And as we talked about in our qualitative analysis section, we're going to have even less be able to dissolve in this condition because we already have a common ion. So we'll have our solubility be even less than 5.8 times 10 to the negative 4. That being said, this number, or a number even smaller, is so much smaller than our already existing amount, 0.10. So let's look at this. I have 0.1. Let's say that our solubility was the same, even though we know it's going to be smaller. I'd be adding 0.00058, right? Together, this is going to give me 0.10058. So if I'm still going to my 2 sig figs, because that's what I had, my answer is still 0.10. Because of this, because my X value is going to be so much incredibly smaller than this 0.01, I can assume that after sig figs, my value is just going to be 0.1. So I'm going to assume here, based on what I know about the solubility in pure water and the fact that this is going to be even less soluble, that because as my x is so much smaller, I can do this with my math. I can drop this plus x because my value is basically just going to be 0.10. This is now my KSP expression I'm going to solve. This is going to make it a whole lot easier. So now I just divide each side by 0.10. I find that x is equal to 3.4 times 10 to the negative 6. I go back to what I let my x be. I let x equal my change, so this would be x here. This is how much was associated. This is a 1-to-1. So this value becomes now my solubility of my strontium sulfate in moles per liter in a solution of 0.1 molar strontium nitrate. So see how this value is so much smaller than the value of pure water. So already this makes sense. I'm adding it to something with a common ion. My solubility is getting smaller. So we're going to do the same thing here, but now in our third condition. So now we're looking at adding our strontium sulfate into a solution of chromium 4 sulfate. We'll make sure that's balanced. So this is my solution that I already have. Now, once again, I'm going to let my x, we'll say my x, let's say it's just the solubility of my strontium sulfate. So I'm going to do an ice table here. I have my strontium sulfate with some strontium and my sulfate. So initially, let me maybe do it this way this time so that you can see what I'm talking about. We're say x, this amount. I have 0 amount of strontium. My sulfate, I already have some. And this isn't for my strontium sulfate. This is actually for my common ion. So if I had 0.1 molar, 1-to-1, so 0.1 molar of chromium 4 ion, however, that is not going to do anything here. Times that by 2, I have 0.2 molar already of my sulfate. So this is coming straight from my common ion that was already in solution. So if all of this dissociates, and remember this is solid, so I really don't need to worry about it, then I'll have plus x and plus x. Now if I had coefficients here, I would have to adjust my change, but since this is a 1-to-1, I'll have plus x for both of these. Then at equilibrium, I have x amount of strontium and 0.2 plus x. So my KSP is multiplying these two together. No coefficients here, so I don't need to worry about exponents. But this will be still 3.4 times 10 to the negative 7. I have not changed the temperature, so no matter what I change my ions to, my KSP value will not change. Is now equal to x times 0.20 plus x. But just like before, if my x is so much smaller than this 0.20, it doesn't matter what x is, this 0.2 is just going to overpower it. After sig figs, no matter what my x value is, this value is basically just going to be 0.2. So because of that, I can simplify my math. with this reasoning, x 0.20. Therefore, I can divide each side by 0.2. I'm left with x. X here is 1.7 times 10 to the negative 6. It is a concentration. This is going to be talking about my solubility of my strontium sulfate. So here, my solubility of strontium sulfate, that is moles per liter, in a solution that already contains 0.1 molar chromium 4 sulfate. So that is my answer here. So let's take a look at all of this solubility. Let's make sure it makes sense with what we predicted qualitatively. So in pure water, I found that my solubility of strontium sulfate was 5.8 times 10 to the negative 4 molar concentration. So in just pure water, my salt here has very low solubility. I can only dissociate 5.8 times 10 to the negative 4 moles for every 1 liter of volume. In my second condition, I expected it to be a lower value, that I could dissociate a smaller amount of ions, and I found that this is correct. I only could dissociate 3.4 times 10 to the negative 6 moles per liter, so a smaller amount. I predicted once again that in chromium 2 sulfate, I would have even less because I'd have double the amount of sulfate that I had strontium ions here. And once again, I see this trend that my solubility has decreased. So these agree nicely with our qualitative predictions. Make sure you know how to do these common ion questions. Please practice. There's quite a lot of questions about them, and the key is posted. But this is the stuff I'm probably going to try to focus on Wednesday during our study session. So please try those, and that's all for now.